Water and air are essential ingredients of climate on Earth. Water vapor easily dissolves in warm air, but condenses if cooled down, originating meteors like rain, mist, snow, or hail. Living beings are mostly made of liquid water, a perfect pot for biochemical reactions. It's well known that temperature conditions their velocity. Most of multicellular living beings do not survive freezing, as ice destroys tissue structures. However, some extreme cases of surviving in very low temperatures strike our knowledge about change of phase in water. Everybody is taught at school that ice melts at 0 Celsius degrees, and water freezes at the same temperature as well. However, it has been well known that liquid water can be supercooled well below 0 degrees Celsius. Down to -40 degree water may remain liquid for a few milliseconds before freezing homogeneously. Supercooled water is a metastable state. Up to now it was assumed that it randomly may freeze without control. This has been recently changed by an unexpected discovery done by a team led by Professor Pérez Díaz of Universidad de Alcalá. They discovered a striking stability in supercooled water solutions, where freezing is exclusively triggered on the water-air interface and conditioned by humidity in air. When they cooled down water droplets, they found that their freezing point depended on the humidity in the air. The lower humidity in air, the lower the freezing point. These experiments show that freezing is clearly triggered on the surface. In fact, the water surface quickly freezes first, creating a shell, and then freezing progresses towards the center of the droplet. As liquid water is compressed, at a certain time it breaks out the shell and is ejected out. Then the surface of this water jet immediately freezes as well, creating a sort of pipesicle. They demonstrated that provided humidity in air is low enough, water solutions can be supercooled down to -12 degrees in liquid metastable condition and preserved for an unlimited time in liquid state. Moreover, when they repeated these experiments using water as a container, they obtained exactly the same freezing point humidity curve. Additionally, with the help of high-speed cameras, they discovered that surface freezing produced two-dimensional crystals on top of the liquid water, and the shape depended on humidity in air. They are like snowflakes on top of the liquid water.
Usually, when we consider the surface of water, we forget about the gas phase. However, water surface is not just the surface of water, but an interface between two media, liquid and gas. And the same stands for the case of ice. The gas phase is completely relevant for the phenomenon that is described in this video. Now consider the different condition of water molecules in liquid and solid. In solid, they are ordered in a crystal structure, while in liquid phase, they keep moving and relatively disordered. Molecules in the gas phase are even more disordered, moving at higher speeds. If we then consider the interaction of gas-water molecules with a liquid surface, they disturb the molecules in the liquid phase, but the effect of this disturbance is relatively small. However, if we consider the interaction of these water molecules in gas phase with the ordered surface of ice, their effect is much more evident, increasing disorder. In physical terms, we can say that the entropy transfer from gas to solid is much larger than that of gas to liquid. This will not be the case of other air molecules like oxygen or nitrogen that are not polar. Essentially, the entropy or disorder of the ice surface depends on humidity in air. A direct consequence is that at certain temperature, the balance of Gibbs energy for freezing depends on humidity in air.
The researcher filed a patent application for a direct use of this phenomenon, supercooled storage of biological material and fresh produces. Experiments with some biological materials demonstrate the same behavior. Their freezing temperature depends on humidity, and they can be stored and preserved for longer time if supercooled. A potential application for this supercooling technique is to preserve organs for transplantation. It seems worth it to try to supercool organs at a temperature well below zero, slowing down ischemia, but simultaneously preventing freezing. In this sense, if a heart is cooled down to -5 degrees below zero, Without freezing, the preservation time could easily be increased in an order of magnitude, maybe a few days, at a really low cost. An increase of 5 hours can multiply by 3 the probability of access to a genetically compatible donor and improve the condition and vitality of the organs.